We have established the need for a fuzzy inferencing technique because we need a crisp number output even when we are using fuzzy rules. So in this video, we're going to take a look at the first fuzzy inferencing technique. The most commonly used fuzzy inference technique is called Mamdani method. It was introduced in 1975 when a professor called Ibrahim Mamdani of London University built one of the first fuzzy systems which was used to control a steam engine and boiler combination. And what he did was, he created a fuzzy set of rules that was supplied by an experienced human operators and applied them in his fuzzy system. Using the Mamdani fuzzy inference, there are 4 steps. The first is fuzzification of the input variables. Second is rule evaluation. Third is aggregation of the rule outputs. And the fourth step is the defuzzification. So let's take a look at an example. In this system, we have 3 rules where we will examine a simple 2 input and 1 output. So the 2 input are related to project funding and project staffing, while the output would be risk. So if you look at the rules, let's look at rule 1. If X is A3 or Y is B1, then Z is C1. And translated into fuzzy rules, if project funding is adequate or project staffing is small, then risk is low. So what you can map here is X is project funding, Y is project staffing, and Z is risk. Meanwhile, A3 is the adequate fuzzy set of project funding. B1 is small fuzzy set of project staffing, and C1 is low fuzzy set of risk. And if you look at rule 2 and rule 3, the rules are a little bit different, but still discussing the same linguistic variables X, Y, and Z. So let's look at the 3 universe of discourse, where capital X is project funding, capital Y is project staffing, and capital Z is risk. So this is project funding. So in project funding, it is made up of 3 fuzzy sets. First one is inadequate, second one is marginal, third one is adequate. And this is with X as the universe of discourse. Okay, the second one is project staffing. It is made up of 2 fuzzy subsets, which is small and large, and the universe of discourse is Y from 0 until 100%. And the risk, Z is related to risk, and this universe of discourse is made up of 3 fuzzy subsets: low, normal, and high. The first step in a Mamdani fuzzy inference is fuzzification. So what exactly this step is all about is, first we need to take crisp input x1 and y1, where x1 is project funding and y1 is project staffing, and we need to determine the degree to which these inputs belong to each of the appropriate fuzzy sets. So if you look at this first figure, figure 1, the crisp input is x1, and you need to remember x1 is project funding. So this is x1 and it falls somewhere here. Now we need to check S1 belongs into which subset. of which fuzzy set? So A1 is inadequate, A2 is marginal, and A3 is adequate. Based on where it is located, A1 has the values of 0.5 in the membership degree of A1. So I repeat, X1 has the membership degree of 0.5 in the fuzzy set of A1, and it has a membership degree of 0.2 in the subset of A2. What this basically means is it is 50% inadequate and 20% marginal. So this is the project funding. Okay, now moving on to project staffing. So this is project staffing. The value of Y1 falls here. So it falls here and it is 10% belonging to B1, where B1 is small. So 10% small and 70% large. So this is talking about project staffing. So the values here is first X1, where X1 has the value of 0.5 in the membership degree of set A1 and 0.2 in the membership degree of A2, and Y1 has the value of 0.1 in the membership degree of B1 and 0.7 in the membership degree of B2. So the value of X1 is both inadequate and marginal, and the value of Y1 is also both small and large. So the second step in Mamdani Fuzzy Inference is to do rule evaluation. So what we need to do is to take the fuzzified inputs in step 1, which in this particular case, we have X has the membership degree of 0.5 of set A1 and 0.2 of set A2, while Y has 0.1 the membership degree of set B1 and 0.7 of set B2, and we need to apply them to the antecedents of the fuzzy rules. And if you still remember, we have 3 rules for this particular case. If a given fuzzy rule has multiple antecedents, we need to use fuzzy operator, and the operators are AND operator and also OR operator, so that we are able to obtain a single number which represent the result of the antecedent evaluations. So this number, the single number, will then be applied to the consequent membership function. So let's take a look at the 3 rules of our case study. This is rule 1, rule 2, and rule 3. And if you notice, in rule 1, we have 2 antecedents. And for rule 2, we also have 2 antecedents. Only rule 3 have a single antecedent. So for rule 1, because the operation is OR operation, we will be using a max of evaluation. As for rule 2, because the operation is an AND operation, we need to do a min evaluation. So going back to the fuzzified inputs that we have processed in step 1, we need to plug in these values into our rules. Okay, rule 1, if X is A3 or Y is B1, and we need to remember that A3 is adequate funding and B1 is small staffing. So X actually has the values of A2 and A3. Therefore, in rule 1, the A3 value of X is 0, because X doesn't belong in the fuzzy set of A3. And the value of B1 is 0.1, and because this is an OR operation, and as for OR operation we need to do max evaluation, so 0.1 map to C1, which is low risk, and we get this area. Okay, now let's evaluate rule 2. For rule 2, if x is A2 and y is B2, then z is C2. So this is the second rule. And our falsified input, x and y, so x has 0.2 as the membership degree of the set A2, which is marginal funding, and y has the membership degree of 0.7 of the set B2, which is large staffing. And because this is an AND operation, we need to evaluate the mean value. So the mean value between 0.2 and 0.7 is 0.2. So what we do is we do a monotonic selection of the value of 0, 2 and map it into C2, because this is what the rule is stating. So this area over here is the result of rule 2 evaluation. And finally, for rule 3 evaluation, it says that if x is A1, then z is C3. X has the value of 0.5, the membership degree of fuzzy set A1, which is inadequate, and we can directly map it into C3, which is high risk. So this area over here is the result of evaluation of rule 3. Now, the result of the antecedent evaluation when can be applied to the membership function of the consequent, which we did just now. What we need to do is we need to correlate the rule consequent with the true value of the rule antecedent, and to cut the consequent membership function at the level of the antecedent truth. So this method is called clipping. Since the top of the membership function is sliced, the clip fuzzy set loses some information. However, clipping is preferred compared to the other method because it involves less complex and faster mathematics. The second technique of getting the result of the consequent is called scaling. Scaling offers better approach because it preserves the original shape of the fuzzy set. So for example, if the fuzzy set is in the form of this trapezoid, if we do clipping, what we do is if the consequent is 0.2, so we are only taking this area over here. So we clip and we take out this space at the top. So if you notice, this space that we are taking, it doesn't look like a trapezoid anymore. However, if we do scaling and the original fuzzy set is in the form of trapezoid, and the result of the consequent is over here, scaling basically we are reducing the shape of the fuzzy set into still the form of trapezoid, but to fit in the value underneath the result of the consequent. So it will still preserve the shape of the trapezoid. Therefore, in this method, it loses less information. However, the mathematical evaluation or the computation power needed to do this operation is higher as compared to just clipping. So if you look here, this is the result of clipping and this is the result of scaling. So if you notice, scaling still somewhat preserve the form of a trapezoid. The third step in Mamdani Fuzzy Inference is aggregation of the rule output. So aggregation, like its name implies, is the process of unification. So what we are unifying is basically the result or the output of all rules. So in our current example, we have 3 rules, so we need to combine the output of all 3 rules. So we take the membership function of all rule consequent that we either clip or scale, and we combine them into a single fuzzy set. And the input of the aggregation process is the list of clip or scaled membership function, while the output is one fuzzy set for each output variable. And if you look at this figure here, this figure is the result of rule 1. This one is the result of rule 2, and this is the result of rule 3. So we will be combining all these 3 into a single output rule. So this is the result of the aggregation. So this is one set. This is the resulting set. So the result of step 3, which is aggregation, is a set of itself. So it is in the form of an area of a graph. However, if we want to use it in a fuzzy system, the final output must be a Cripps number, just like our input at the very beginning of this whole process. Therefore, the fourth step is called defuzzification. The input of the defuzzification process was, the input of the defuzzification process is the aggregate output fuzzy set that we have processed in step 3, and the output would be a single number. So in order to find this Cripps value as output, we need to do defuzzification, and the most popular technique is called centroid technique. So centroid technique is where we find a point in the aggregate set where if we draw a vertical line, it will slice it into 2 equal meshes. So for example, if I have a triangle and I draw this line that would equally distribute these 2 meshes. So this is the COG, or the center of gravity, and it can be expressed as this mathematical equation. So if you notice, this is basically some integration formulation or integration operation and to find area. So centroid defuzzification method would find a point representing the center of gravity of the fuzzy set A on the interval AB. So this whole thing, this whole set over here is fuzzy set A, and from A to B is our interval. Therefore, a reasonable estimate can be obtained by calculating it over a sample of points. So this method over here is a method of calculating area using numerical method, which is much easier as compared to integration. So looking back to the result of our step 3, so this graph over here is the aggregation of all the clip output of our rules. So this is a result of rule 1, the aggregation of rule 1, rule 2, and rule 3. So if we want to calculate the center of gravity for this particular fuzzy set, what we do is our values is from 0 until 100, and we separate this area into a certain section. So if you notice, our set is divided into sections of tens. Okay, 10, 20, 30 up until 100. In order for us to calculate the center of gravity, we need to do some calculation, and we need to consider the membership degree of all the sets. And if you still remember, this one is the clipping of the result of C1, this is C2, and this is C3. C1 has the membership degrees of 0.1, C2 membership degree of 0.2, and C3 the membership degree of 0.5. So we'll calculate the values by looking at, in the area of C1, this is C1, what are the intervals that falls under C1? So the intervals are 0, 10, and 20. We sum all these values together and we times that with the membership degrees of 0.1 because it falls under C1, and then we sum the value of 30, 40, 50, and 60 because they are all falls under C2, and we times that with 0.2, and we add them together with 70, 80, 90, and 100 because this all falls under the set of C3 and times that with the membership degrees of 0.5. Okay, all these values needs to be divided with this set of values. And how do you get this set of values? So if you see, we are doing a summation of values of 0.1, 0.2, and 0.5. And where do we get these values and where do we get these numbers? So this value 0.1 is added 3 times because there are 3 0.1 in the set of C1. Okay, this is 1 and 2 and 3. And then as for 0.2, it is added 4 times because there are 4 we have 4 intervals under the set of C2. So this is 1, 2, and 3, and 4. And the membership degree is 0.2. That's why we are adding 4 of 0.2. And therefore, as for 0.5, which is the membership degree of set C3, there are 4 intervals of 0.5, so 0.5 is added 4 times. And then the result of this whole operation is 67.4, which is a crisp value. What is the disadvantage of Mamdani Fuzzy Inference? First of all, it requires the computer to find the centroid of a 2D shape by integrating across a continuously varying function. In general, this process is not computationally efficient, and you have to remember when we are developing AI function, computer resources is very precious. Therefore, there is an alternative to Mamdani Fuzzy Inference, and we will discuss that in our next video.